Today on AI Paper Podcasts, we're jumping straight into a paper that completely rethinks how robots understand the world. It's by Hans Zhao and a team of researchers, and it's called FRAPPE.
Right, which stands for Future Representation Alignment via Parallel Progressive Expansion.
Exactly. And if you are working in robotics or generalist policies, listen up, because this solves what the authors call the pixel trap.
Yeah, that's the big hook here.
Instead of burning massive amounts of compute trying to generate these high-fidelity, pixel-perfect future video frames, which causes hallucinations and just slows everything down, FRAPPE teaches robots to predict the latent representation of the future.
It's a fundamental shift. They use a mixture of experts approach called MAPA. That's a mixture of prefix and LoRa.
Right.
And it essentially aligns the robot's policy with multiple visual foundation models. So we're talking Sleeklet, DynoV2, and VTL simultaneously during training.
And the results are wild. State-of-the-art performance on the RoboTwin benchmark, beating Google's Pi 0 and Pi 0.5. But maybe most importantly, they get a 10 to 15% performance boost using cheap, action-free videos from the internet.
Yeah, that data scaling aspect is huge. Right. It's basically a blueprint for scaling robot learning without scaling the insane cost of teleoperation.
All right, so that's the 1-minute summary. Let's unpack the details of this deep dive.
Sounds good.
So to really appreciate what FRAPPE is doing, we have to start with the current status quo. Right? The massive headache that is building generalist robotic policies today.
Right, because right now the whole field is basically rallying around diffusion transformers. Models like RDT, the robotic diffusion transformer.
Yeah, and the prevailing logic for getting these models to understand the world, to have world modeling, has been video generation.
Which makes sense on paper. The idea is if a robot truly understands its environment, it should be able to predict exactly what its camera is going to see next. You give it a state, you give it an action, and it spits out the next frame.
It sounds totally logical. Like if I push a coffee cup off a table, the model should just generate a video of that cup falling.
It sounds logical to us, yeah. But for a neural network, it is incredibly inefficient. This is what the paper explicitly calls the pixel trap.
The pixel trap.
Exactly. Because to generate a realistic video frame, the model has to burn a massive number of parameters just rendering things that don't matter.
Like background textures.
Right. Background textures, lighting changes, shadows, things that have literally zero impact on the physics of the actual task.
The paper calls those redundant pixels.
Redundant pixels, yeah. Like whether the fluorescent light reflects perfectly off the fridge in the background, that doesn't change whether the robot's gripper is successfully closed around the apple.
Right.
But if you're using a video generation objective, your loss function is penalizing the model if it gets that reflection wrong.
Which is just a massive waste of gradient updates on aesthetics.
Exactly. You're teaching the robot to be a filmmaker instead of a worker.
And it's not just an efficiency problem, right?
Yeah.
The paper points out this causes major stability issues during inference, error accumulation.
This is the real killer for deployment, because these are autoregressive models. They predict frame 2, and then they use frame 2 to predict frame 3.
So frame 2 is just slightly off.
Right. If there's a tiny visual artifact, maybe the edge of the object is a pixel too far to the left or it's a bit blurry, that error gets fed right back into the model.
And it compounds. Suddenly the object starts teleporting.
Teleporting, warping, melting. By frame 10, your model is hallucinating obstacles that aren't even there in the real world.
And if your robot's control policy is reacting to that hallucinated video plan, it's just going to fail. It's going to crash into a wall.
Exactly.
Now, there is a third limitation they bring up with current models, which I think is fascinating: single view bias.
Yeah, this is a really critical point for the ML engineers listening right now.
Because some people have already figured out that generating pixels is bad, right? So previous work tried to bypass this by just aligning the robot with a pre-trained encoder.
Right. They'd say, don't predict the image, just predict the embedding that CLIP would produce for that image.
Which solves the redundant pixel problem. CLIP doesn't care about the lighting on the fridge.
It solves the pixel problem, but it introduces a new one. CLP has a massive inductive bias. It's a semantic model. It's amazing at knowing, hey, this is a coffee mug.
Right.
But it's actually pretty terrible at precise geometry or spatial relationships. It doesn't really know exactly how the handle is oriented in 3D space.
And for a robot trying to grab that handle, geometry is kind of important.
Very important. Now, conversely, if you align your robot with DynoV2 instead of CLP, you get fantastic geometry and spatial awareness.
But you might lose the semantic context.
Exactly. So if you rely on a single visual encoder, a single teacher, You are baking that teacher's blind spots directly into your robot.
You're giving it a learning disability. It's either going to be bad at spatial math or bad at identifying what things actually are.
Right. Which finally brings us to their solution, FRAPPE.
Future representation alignment via parallel progressive expansion. Let's get into the architecture, because the core philosophy here is brilliant. Don't predict the pixels, predict the meaning, and don't just use one teacher. Use all of them.
It's a classic mixture of experts approach, MOE, but applied entirely in the latent space.
So they build this on top of the RDT1B backbone, right?
They do, and this is a huge detail for anyone worrying about training costs. They keep that massive backbone frozen.
Oh, wow. So they aren't retraining a billion parameters from scratch.
No, not at all. They inject new lightweight modules into it. This is the MAPA architecture we mentioned earlier.
The mixture of prefix and LoRa. Break that down for us.
So they use two mechanisms to inject this awareness of the future. First are the prefixes. These are basically just learnable tokens appended to the input sequence. They act as placeholders.
Placeholders for the future states the robot is trying to predict.
Exactly. And then you have the LoRa modules, low-rank adaptation. We see this everywhere in LLM fine-tuning now.
Yeah, it's standard practice.
Right. So they insert these LoRa matrices into the transformer blocks. But the twist, the MOE part, is that they create parallel sets of these modules.
Ah, okay.
So one set of LoRa adapters is the CLIPE expert. Its only job in the world is to predict the embedding vector that CLIP would generate for the future frame.
And then another parallel set is the Dino expert.
You got it. And a third set is just a standard VIT expert.
So instead of the model spitting out a JPEG, it's outputting 3 distinct mathematical vectors.
Right. And the loss function, they call it the alignment loss, is super elegant. It just calculates the cosine similarity between the robot's predicted vector and the actual vector produced by the real teacher model.
While looking at the real future frame.
Yes. They put a stop gradient on the teacher, obviously, so the teacher doesn't change. It's pure representation alignment.
No decoder required.
None.
But wait, how do they actually manage these experts? Because if I have the CLIP expert shouting about semantics and the Dino expert shouting about the geometry of the cup handle, how does the robot know who to listen to?
That is where the router comes in.
Okay.
It's a very lightweight neural network, a gating mechanism. It analyzes the current context of the task and assigns weights to each expert.
Oh, I see. So it's dynamic.
Highly dynamic. If the instruction is highly semantic, like pick up the red block and ignore the green block, the router learns, okay, semantics are key here. I need to weight the CLIP expert's output much higher.
But if the task is something requiring insane precision, like insert this tiny peg into that exact hole,
then the router dynamically shifts the weight over to the Dano expert. It learns which representation is most useful for that specific millisecond of the task.
that makes total sense. Now, there is a technical detail in the paper about load balancing, because anyone who is trained in MOE knows about mode collapse.
Oh, yeah. It's the bane of mixture of experts.
You always end up with one expert just doing all the work and the others just sit there.
Right. Without intervention, the router might just decide, hey, the VIT expert is generally good enough for most things, so it sends all the signal there early in training.
And the CLAP and Dino experts just starve.
They starve, their gradients dry up, and they learn nothing. So the FRAPPE team implemented a load balancing loss.
How does that work in this context?
It's an auxiliary loss term. It basically penalizes the router if the distribution of its weights becomes too skewed towards one expert.
So it forces the router to spread the wealth.
Exactly. It forces it to keep all the experts engaged, which guarantees you get that diverse multi-view representation. They also use label smoothing on the router weights just to keep things extra stable.
That's super smart. Okay, let's talk about the actual training recipe, because they didn't just plug this all together, press play, and watch it work.
No. They actually noted that direct scaling failed pretty badly.
Right. Jumping straight to parallel experts caused massive convergence issues.
It's a classic curriculum learning problem. Think about it. The base RDT model was pre-trained just to denoise actions. Suddenly, you're asking it to simultaneously predict future embeddings for 3 totally different visual distributions using these tiny LoRa modules. The distribution shift is just too violent. The optimization landscape is too jagged.
So they had to break it into a 2-stage training recipe. Let's look at stage 1. They call it mid-training.
In mid-training, they simplify the problem. They don't use the parallel experts at all. It's just a single stream. And they align the robot with a single unified teacher called Thea.
Thea? I don't think I've heard of that one. Is that a new foundation model?
It's actually a distilled model. The authors essentially pre-cooked a super teacher for this stage. They took multiple visual foundation models and distilled all their knowledge into one single encoder. That's Thea.
Okay, so it's a stepping stone.
Exactly. And the crucial detail here, the really important part, is that during this first stage, they use full parameter fine-tuning.
Oh, so this is where they unfreeze the backbone.
Yes, they unfreeze the whole billion parameter beast because they need the robot's brain to fundamentally rewire itself. It has to shift its core objective from just action denoising to actual world modeling.
It's building the bridge between those two concepts.
Precisely. And then once that bridge is built, we move to stage 2, post-training.
The parallel scaling phase.
Right. Here they freeze the backbone again. They swap out Thea for the parallel MAPA architecture, so now you have the separate CClip, Dino, and VVAT teachers, and they only train those prefix and Larara modules.
Which is incredibly parameter efficient.
Very. You're just refining the specific eyes of the model without destroying the motor cortex you just spent stage 1 building.
Okay, I want to shift gears to the data strategy, because honestly, for the engineers listening, this might be the most economically valuable part of the entire paper.
It really is. We all know about the data wall in robotics.
It's the bottleneck. Teleoperation data, having a human physically control the robot to teach it, is so expensive and slow.
Painfully slow. You're lucky to get, what, maybe 120 trajectories an hour?
Yeah, it doesn't scale. So FRPPE introduces this data pyramid concept to get around it.
Imagine a pyramid. The bottom layer, the widest part, is built entirely on action-free data.
Meaning videos of humans doing things, but without any robot control commands attached.
Right. They use this data set called TasteRob. It's over 100,000 internet egocentric videos of people just doing everyday tasks, opening drawers, using tools, chopping vegetables.
But the robot doesn't know what the motor commands were for those actions. It just sees pixels changing.
Exactly. And in a standard behavior cloning setup, that data is completely useless. You can't calculate an action loss because there is no action label to compare against.
But FRPPE has a loophole.
It has the alignment loss.
Right.
For this bottom layer of the pyramid, they just turn off the action loss entirely. They treat the video purely as a world modeling exercise. The robot watches the human hand move left, and it predicts the future embedding where the cup moves left.
So it's literally just learning the physics engine of the real world.
Yes, it's learning dynamics. It learns that if you drop a cup, it falls down, it doesn't fall up. It learns that solid objects don't pass through other solid objects.
And it's learning all of this generalized physics from cheap, basically infinite YouTube-style data. That's incredible.
It really is. Then you move up to the middle layer of the pyramid.
Task-specific human videos.
Right. So this is a smaller data set, but it's focused on the exact job you want the robot to do. Like a human doing a specific assembly task. Again, no tele-up data, just video.
And finally, the very tip of the pyramid is your expensive robot teleoperation data.
Exactly. And the magic here is co-training, because the model has already learned general physics from the bottom layer and the specific task dynamics from the middle layer. It needs drastically less teleop data to figure out how to bind those concepts to its own physical motors.
It's almost like teaching a pilot to fly by having them sit in a flight simulator and watch out the window for 100 hours. By the time they actually touch the joystick, they already intuitively know what pitching up looks like out the window.
That is a perfect analogy. You are completely decoupling the understanding of the task from the physical execution of the task.
Which just fundamentally changes the math on how we scale robot data. All right, let's look at the scoreboard. They put this through the ringer on the RoboTwin benchmark.
They did. And RoboTwin is a great testing ground because it has very distinct easy and hard settings.
And the hard setting is where things usually fall apart, right?
Okay.
Because of domain randomization.
Yeah, the hard setting throws everything at the model. Lighting shifts, lots of table clutter, changing the height of the table entirely. This is where baseline models just crumble because their visual representations aren't robust.
So how did FRAPPE hold up?
It absolutely dominated. If you look at the hard setting, specifically for a complex task like put object in cabinet, the baseline RDT model scored around 15% success.
Okay, 15%. And FRPPE?
FRPPE jumped to 37%.
Wow. So more than a 2x improvement on a highly randomized task.
And it even outperformed Google's Pi 0.5 model on the aggregate hard scores, which is no small feat. It strongly suggests that this MOE latent approach isn't just a clever trick. It genuinely provides a multi-view understanding that resists noise.
But they didn't just stay in simulation, did they? The real-world experiments on the Agilex mobile manipulators are what really caught my eye.
Oh yeah, the real-world stuff is where the rubber meets the road.
Specifically, they did this long horizon task, the pot, lid, and vegetable task.
Right, so this is a complex sequence. The robot has to pick up a vegetable, put it in a pot, then go pick up the lid and place the lid on the pot.
Which requires serious temporal continuity.
Exactly. If the robot forgets the state of the vegetable by the time it reaches for the lid, the whole task fails.
And the baseline RDT model?
Failed completely.
Yeah.
0% success rate. It just couldn't handle the compounding visual errors over that long of a time horizon.
And FRAPPE?
FRAPPE achieved a 20% success rate.
Now, I can already hear some skeptical ML engineers listening to this saying, okay, 20% means it's still failing 80% of the time.
Sure, but you have to look at the context. In the realm of zero-shot transfer or low-data regimes, for long-horizon physical robotics, going from 0% to 20% is massive. It's the difference between a system being fundamentally broken and a system that actually works.
Right. It proves the signal is there.
Exactly. It proves the world model is actually maintaining coherence over time. Taking a model from 20% to 90% is mostly an exercise in engineering and scaling. But that fundamental 0 to 1 roadblock, FRAPE, solved it.
Speaking of engineering, we have to talk about the cost of running this. Because you've got 3 visual encoders, the router, the backbone. Is Inference just painfully sluggish?
Surprisingly, no. They were very clever about optimizing the inference pipeline. They used CDA graphs to run all the parallel experts simultaneously.
Oh, nice.
Yeah. So the actual latency penalty compared to just running vanilla RDT was only about 20 milliseconds.
The 20 millisecond, that's barely a single frame at 30 frames per second.
It's completely negligible for real-time control. And memory-wise, the whole setup fits on an 8-gigabyte VRAM card.
Seriously, you can run this on a consumer GPU.
You can. They even did an ablation study where they demonstrated the architecture on a much smaller 130 million parameter model, and it scaled down beautifully while still beating baselines.
So we have a system that learns physics from cheap YouTube videos, aligns with multiple state-of-the-art vision models simultaneously, resists visual noise, and runs on consumer hardware.
It's a very, very compelling package.
So what's the ultimate takeaway for the researchers listening today? Is explicit pixel generation officially dead for robotics?
I wouldn't go as far as saying it's dead, but this paper definitely exposes it as a massive detour.
Yeah.
We spent so much time in compute trying to make robots into good visual artists. FRAPE proves that robots don't need to be artists. They don't need to paint the scene. They just need to understand the plot.
Right. Aligning with latent experts is cheaper, it's faster, and it's evidently far more robust to the messy reality of the physical world.
And that data pyramid we talked about, that feels like the key to unlocking the next order of magnitude and scaling. If we can truly use the internet's entire video archive as action-free pre-training data, we effectively unlock continual pre-training for robotics.
Which is the holy grail.
It is. A robot could be constantly learning about new objects, new environments, and new physics, 247, without a human ever having to put on a VR headset and teleoperate it.
Which actually leads me to a really provocative thought to close out on.
Right.
Right now, FRAPE aligns the robot with vision models, CLI, Dino, VIFT.
Great.
But what happens when we scale this up to align the policy with massive multimodal reasoning models, like GPT-4V or Gemini?
Oh, man. That is a logical next step.
Right. If you can distill the explicit reasoning capabilities of those massive models directly into the latent control loop of a robot.
Then you aren't just teaching a robot where the coffee cup is. You're teaching it why the coffee cup is there and what to do if it spills.
Exactly. It goes from physical dynamics to actual cognitive understanding. And that is a future definitely worth building toward.
Absolutely.
Well, we will wrap it up there for today. For everyone listening, you can find the link to the FRAPE paper in the show notes. Definitely go read it. The architecture details are fantastic.
Thanks for having me.
Catch you on the next one.